Professor Clements with you as we study electrostatics in this video, covering some of the basics of the nature of electricity when there's no movement of the charge along a wire. We'll study currents in future videos, and we'll talk a little bit about Coulomb's law of the force of electrostatics. Now here you see a child going down a slide. The friction with the plastic material on the slide has caused a separation of charge, and the electrons are the charges that are moving around. So we have in this particular case, with the materials involved, the clothing and the plastic of the slide here, so we get electrons moving to the plastic preferentially, leaving a net positive charge, and the child's hair, these strands have positive charges that are repelling each other. So there's one example of electrostatics. Possibly you've walked across a carpet and have felt a spark as you touched a doorknob. Be another example of electrostatics, where you have separation of charge. Now the static part to it, there will be pushing charges around, but no long-term motion of charge. So we call that electrostatics, even though there is some separation of charge occurring in these examples. Ben Franklin possibly did dangerous experiments like this. Do not attempt this. Flying a kite in a thunderstorm, very dangerous. With the string, a wet string can be a conducting path for that lightning stroke, but Benjamin Franklin did various experiments with electricity. Unfortunately, it turns out he had a misconception. Following the theories of heat and the quantity called the caloric that was thought to make objects hot or cold before 1800, that body of knowledge was existing for Benjamin Franklin, and he sort of carried it over and proposed that electricity was only positive charge, and that one sign of this positive charge, or indication of this positive charge, if there was too much of it, we call that object positive. If there's too little of it in the object, then we call it negative. That is not correct. There are two charges, a positive charge, and for atoms that's the proton, and the negative charge carried by the electron. So Benjamin Franklin got us started off a little bit, and there's a situation regarding current and wires, notation that is still wrong based on how Benjamin Franklin decided to identify the charges. So again, look for that when we talk about the unit on electricity. Static electricity has been observed for a long time. We get the information of static electricity, or we get examples of static electricity with the amber as kind of a substance that will preferentially gain electrons when it's again rubbed on a cloth. So static electricity has been observed for quite some time. We can do some experiments, of course, and gain further understanding into the nature of electrical force. Here we have a glass rod and silk, and when the two objects are rubbed together, it turns out that the silk preferentially will take more electrons away from some of the atoms of the glass, leaving the glass with a net positive charge and the silk with a net negative charge. There's something called conservation of charge in play here. When this occurs, if we would put the objects back together and look at the net charge, it would be zero. In an atom, there's a balance most of the time between the number of protons and the number of electrons, and the net charge is balanced as well, neutral. But we can separate the charges, and we get a certain amount of positive charge here. We get the equal number of negative charge over on the silk. If we do this to two glass rods, we can observe a force. Like charges repel. Like charges repel. Positive repels positive, and the two silk cloths will repel each other if they're light enough that gravity doesn't make the observation difficult. We would see the two negative charges repel each other. So that's an observation of electrical force. positive charge repels positive charge, negative charge repels negative charge, and it is true that positive charge is attracted to negative charge. The atom is what's causing this for these type of experiments. This is a rough model of the atom. Don't get too attached to this. The electron does not move in orbits like planets around the sun. The electron does not move in orbits around the nucleus. But that's a further video down the road when we talk about the atom. But it is true that the electron, for some atoms, can be easily pulled away from the atom. And that gives us this electrical effect of the electrons moving onto the silk and the ion now, the positive material, being left in the glass. The electrical force does keep the electron in the vicinity of the nucleus, the positive nucleus, the negative electron, and there is an attractive force that makes this work. It's not quite represented by this picture. There are two types of charge. The electron carries negative charge, the proton carries positive charge, and there are other particles we'll talk about later in the semester that also have this property of charge. But let's move ahead. Van de Graaff generator, or there's a mechanism here that causes charge to pile up. The human body is somewhat of a conductor for the charge, and again, a person's hair will stand out, being repelled from each other because like charges repel. The proton is built up, excuse me, the proton is built up of quarks that have fractional charges, but very, very difficult to separate one quark from another. And this course will not worry about this, but our proton has a net charge of +1 unit of charge. And there's been a determination of that number in terms of the metric unit of the Coulomb. We'll talk about that in just a minute. But the proton there's good evidence that it's built up of these three quarks. If you add these up, +4/3 -1/3, that would be a +1. The electron is not made up of quarks. The electron is more of a fundamental particle than the proton. So here again we have the illustration of separation of charge and the conservation of charge being indicated. If we take 2 units of charge away from the amber onto a cloth, it has -2, the net is 0. If we take 3 units of charge away, there would be -3 on the cloth, the net is 0. Charge is always conserved in any process. We cannot create a single negative charge, nor can we create a single positive charge. In the universe, every process obeys this law of conservation of charge. The charge of the universe is unchanged as various processes occur. It is possible to create mass from light, and in doing this, if light engages in this probability, there's some probability this will occur. If light becomes mass, then we're going to create a positive particle and a negative particle. This showing the electron and the anti-electron, antimatter, but it has a positive charge. It's just like the regular electron, but it has positive charge. And if these two approach each other, matter and antimatter, they can annihilate and become energy. So this is E = mc², going in both directions, showing this here. Let's back up just a little bit and talk about this electron. In the late 1800s, with vacuum tube technology being developed, physicists noted that this particle was moving through the vacuum tube. They called it a cathode ray at first because it came from the cathode, the negative terminal in the vacuum tube, and they measured the ratio of the charge of the electron to the mass of the electron by how well it moved in a circle, what size circle it moved in a certain magnetic field. We'll get to that later too, and how the magnetic force applies to charged particles. But in the early 1900s, a physicist by the name of Millikan did an experiment by using small oil drops between a plate that was charged positive and a plate that was charged negative. And Millikan would watch these oil drops. They had some of them would have a net charge on them, and he could watch them move in the presence of electrical force and gravity, and worked out calculations on how much charge was on the electron, and came up with the number, roughly 1.6 times 10 to the minus 19 coulombs. 1.6 times 10 to the minus 19 coulombs. So that's our fundamental unit of charge. And it's a negative when it's on the electron. It's a positive 1.6 times 10 to the minus 19 on the proton. The two objects have the same magnitude of charge, but the electron is negative and the proton is positive. So this scientist Millikan did this oil drop experiment early 1900s. It is interesting. He grew up in eastern Iowa. In fact, grew up in my wife's hometown. So I went to high school there and then went on to university and did very good work. This is sort of a historical time, the early 1900s, when science in the United States is getting to be on a par with science in Europe. Scientific activities were developing here. So, to conductors and insulators. The wire and the plugs here, those are conductors, metals. In a metal, roughly each atom has one free electron that's able to move easily throughout the metal. So that's a conductor. The insulator, the rubber here, the atoms in the insulators hold on tightly to all their electrons. And it's very difficult for an electron to leave an atom of an insulating material. So wood, rubber, glass, etc. The electrons are bound. But in conductors, gold, silver, copper, aluminum, iron, the electrons can move more or less freely through the material. There is resistance to the motion. We'll talk about that in a future chapter. But that's the basic difference between conductor and insulator. Atoms of elements that conduct have one electron that's free to move, more or less. And insulators, the electrons are bound. So this has a shared property with the conduction of heat. If you're cooking, you use a wooden spoon to stir some boiling water and not a metal spoon because the wood atoms hang on to their electron. It's more difficult for the electrons in the wood to carry kinetic energy from the hot water up to where your hand is. But it's relatively easy for the electrons in a metal spoon to carry kinetic energy by collisions from one atom to another and up to your hand. So we have conductors and insulators. Here's an electroscope. An electroscope is a device where there's a metal ball at the top, a rod that comes down through an insulating ring. So the metal rod here is not in electrical contact with the shell of the electroscope, but the rod comes on down, and then there are two very light leaves that hang from the support. So if we bring a positive charged rod towards this electroscope, this is a metal, the electrons that are able to move, some of them will move to the top, leaving a net positive charge at the bottom, and now the two leaves repel each other. If the rod actually touches the electroscope, some of the electrons will move on to the glass rod, and again, we'll have a net charge in the situation. Some of the electrons have left, and we'll have a net positive charge remaining on the electroscope even when the rod moves away. But the electroscope is a nice, handy, quick device to give us evidence that net charge is present. We won't take any measurements with this really in lab, but we'll see the presence of electrical charge. We can have two spheres in contact. If we bring up a glass rod, again positively charged, it's going to attract electrons and try to draw them over. But this air is somewhat of an insulator until the difference in charge becomes too great. We get a lightning stroke. But for kind of lab activities, we'll get an air gap here that's an insulator. So the electrons are pulled to this side of the object, but they don't jump onto the rod. Then if we would move the spheres apart, now we have a net electrical charge of negative on the left sphere, a net electrical charge of positive over here. And now we move the rod away, and the charges will try to get back together, but they cannot. And don't be misled by this diagram. The positive charges are not moving back and forth in the metal. The positive charge is the proton. It's buried deep inside the atom. Those atoms are locked in the structure of the material. So when this says positive over here, that's because we have electrons that have left those atoms, leaving them with a net positive charge. And down here, the positive atom has not moved across. Instead, electrons from this side have moved back off to the right, leaving the atoms over here with a net positive charge. So when you think about the process going on here, only the electrons move in a conductor. The positive charge is not moving. In a solid, only the electrons are moving, not the positive protons. So charging by induction, that's basically, it was the previous slide as well as contact, but charging by induction, we bring up a positive charge here. We will attract electrons to here. If we connect to ground, the earth, or a human body is a supply of charge as well. If we do that, electrons will come out of the ground or from the human body and supply more electrons here. And then we pull the rod away, and now there's a net negative charge left on the object. Charging by induction always leaves the opposite sign of charge compared to the rod that we bring up. If we would bring up a rubber rod that has an excess of electrons on it, it would push electrons away. Electrons would be pushed down to the ground or into a human body that's touching here. And then there would be positive charge left, a net positive charge when we're done with the induction, charging by induction process, because some electrons were pushed down to the ground. Then we break this ground connection to this slide C, and the object would have fewer electrons than before. It would be a net positive charge. That's charging by induction. You always get the opposite sign of charge. We can have polarization of charge in materials, and that's illustrated here as the charges separate. Water is a polar molecule. If we bring up a rubber rod with the negative charge on it, the thin stream of water going down, you can see the evidence of the electrical force. In the universe, gravity is more important than electrical force for large objects. Basically, large objects are electrically neutral. So these galaxies here, it's gravity that's causing the mass of the two galaxies to be distorted, the gas and the stars to be deflected off of their paths, and this happens over millions of years, these types of galaxies collisions. But it's gravity that's important because for bulk objects, the objects are usually neutral. If we talk about just the electron and the proton, the gravitational force is roughly 10 to the 40th times weaker than the electrical force. Gravity force is roughly 10 to the 40th times weaker than the electrical force. So you have to have an electrically neutral object really to see gravitational effects. That is the case for most bulk objects. Now, Coulomb, late 1700s, studied the electrical force, and using equipment he was able to make measurements of that force. But first, the basic observation: if we have two negative charges, they repel each other directly away from each other. There's a distance r that's measured center to center. If we have a negative charge and a positive charge, they attract each other. And it does turn out that the force decreases as the distance increases. Force decreases as the distance increases. Here we have two charges, one with a single positive charge, the other double charge, and force is repelling. Here we have the same positive charge, but now 4 negative charges, and the force is larger, and now it's attractive because we have opposite sign charges. Coulomb studied this, and he was able to come up that the electrical force was equal to a constant, K, times Q1 times Q2. The Q's are the charges of the two objects in coulombs. K has a number 9 times 10 to the 9th when we use standard metric units, and it is a constant. And then we divide by the square of the distance between the centers of the two objects, and this R is measured in meters. The force will be in newtons, and This force will be directly on a line towards the centers or away from the centers of the two objects. It is a vector. We must keep track of the vector direction as well as the size in newtons for the calculations. So Coulomb's law, electrical force is equal to 9 times 10 to the ninth times the first charge in coulombs times the second charge in coulombs, and divide by r squared. And for different calculations, these numbers are going to be small. 10 to the minus 10, 10 to the minus 12 coulombs is not unusual. 1 coulomb of charge is a tremendous amount of charge. So it's more typical in real situations to have 10 to the minus 10, 10 to the minus 12 type size. That's where we're going to end this video. Look for some other videos working sample problems. And of course, write down questions and ask your instructor.